Welcome to the Explainer. Now, if you've ever walked through a data center, you've definitely seen those massive cooling cabinets lining the walls. And on the outside, they look absolutely identical. Same fans, same raised floor connections. But open them up, and they actually operate in fundamentally different ways. Today, we're going to demystify exactly how they work under the hood.
Okay, let's dive into this. Here is our structural roadmap to untangle these acronyms step by step. First, the data center heat problem. Then, CRAC, refrigerant-based cooling, followed by CRH, chilled water systems, a head-to-head CRAC versus CRAH compared, and finally, AI and future cooling needs.
Section 1. The data center heat problem. Because, unlike people, servers never actually go home. They just sit there generating immense amounts of heat, continuously.
So, you might be wondering, why not just use normal AC? Well, traditional HVAC is really built for what we call comfort cooling, managing moderate heat and humidity from people in an office. But data centers demand precision cooling. These servers are generating a massive, constant heat load 24/7, which means we need systems specifically designed to blast cold air through dense hardware without fail, just to keep the internet running. Because if we get this wrong, the stakes are literally catastrophic. Even a tiny temperature rise triggers thermal throttling, where servers intentionally slow themselves down just to survive. Left unchecked, you're looking at reduced hardware lifespans, sudden equipment shutdowns, or complete system failures. It's completely unacceptable. And this is exactly why just dropping the thermostat doesn't cut it. Precision cooling manages temperature, airflow, and humidity. It's not just about making the room cold, it's about constant heat removal and maintaining perfectly stable, redundant environments every single second.
Let's move to Section 2, CRAC, refrigerant-based cooling. We're going to see exactly what happens under the hood of our first foundational system.
CRAC, CRAC. This stands for Computer Room Air Conditioner. Think of it like a massive, hyper-precise version of a traditional direct expansion, or DX, HVAC system. It's a self-contained cooling unit packed with its own direct expansion refrigeration circuit, compressors, and expansion valves built right into the cabinet.
So here is the journey of the air, step by step. First, the unit actively pulls hot air right from the data center aisles. Next, that air passes across a really cold, refrigerant-filled evaporator coil. Then, the crisp, cooled air is supplied right back into the room. And finally, all that absorbed heat is pumped away and rejected outside via a condenser.
So the crucial point is a CRAC unit actively creates its own cooling internally, because the active refrigeration components and compressors live right there inside the cabinet. It operates as a completely independent, self-contained air conditioner.
Which brings us to Section 3, CARH, chilled water systems. And yeah, I know, this is exactly where these industry acronyms start causing some serious confusion.
CRAH, CRAH. This stands for Computer Room Air Handler. The distinction here is absolutely vital. A CRAH relies entirely on chilled water pumped in from a central chiller plant. There are absolutely no compressors and no refrigeration circuits inside this specific cabinet, none.
Without a compressor, the internal airflow journey changes. Massive fans pull the warm return air in. Then, they simply pass that air across a coil filled with chilled water coming from the roof or an outside plant. The newly cooled air is blasted back into the data center, while the now warmed water returns to the central chiller plant to be cooled down all over again.
So, to reiterate our core motif with some enthusiasm here, a CRAH unit transfers cooling from somewhere else. It doesn't create the chill itself, it merely acts as a handler to seamlessly transfer that heat to a central outdoor plant.
Section 4, CRAC versus CRAH, compared. Now we're going to put these two foundational solutions head-to-head to see exactly where and why each is used in modern infrastructure.
Here is the real aha moment. CRAC creates cooling using refrigerant versus CAAH, which transfers cooling using chilled water. It sounds so simple, right? But this single fundamental distinction dictates how entire facilities are engineered from the ground up.
And this brilliantly illustrates the divide. Looking at the mechanism, CRAC uses compressors and refrigerant, meaning it operates entirely independently. That makes it perfect for smaller, enterprise facilities. CRAH, however, relies on a chilled water coil, so its use case,
Massive, hyperscale data centers. Because at that massive scale, the centralized nature of a CRAH system becomes incredibly energy efficient. Section 5. AI and future cooling needs. Just as we mastered these air-based systems, a rapidly accelerating new challenge hit the scene.
Modern AI GPU clusters generate extremely high heat loads. We're talking mind-boggling amounts of heat as rack densities skyrocket. Traditional server environments just don't run this hot, which means our legacy air cooling systems have to remove significantly more heat, and honestly, they're struggling to keep up.
Because water transports heat far more efficiently than air ever could, the industry is physically pushing past traditional CAAH limits. To handle AI, facilities are adopting advanced high-density liquid cooling solutions. We're seeing direct-to-chip liquid cooling, rear-door heat exchangers, and even completely wild immersion cooling systems where the hardware is literally submerged in fluid. Which leaves us with a massive infrastructure question. As hyperscale AI models evolve and grow infinitely hotter, are we actually reaching the absolute limits of air cooling? The shift to liquid is really just getting started. Think about that the next time you ask an AI a quick question on your phone. There is a massive hidden world of precision engineering working absolutely overtime just to keep that answer cool. Thanks for tuning into The Explainer, and I'll catch you next time.